Hi guys, welcome to Learn Electronics Repair. In this video we're going to do something a little bit different. I mentioned this on a previous video which we were building a PCBWay project. So this is the project we built. This is a USB load. You can plug this into a USB port and you can vary the adjustment here and you can put a load up to about 7 amps. So I built this and it actually works. But the project on PCBWay has no schematic. And I said in the comments a little while ago that I would show you guys how to take a PCB and make a schematic from it. This is quite a simple PCB, but at the end of the day, this is the best place to start. Once we've reverse engineered this, we'll look at how we can actually improve this. We can add some extra features to it. So just before we do this, let's visit PCBWay.com and I will show you briefly around the sponsor's website. PCBWay are a premium printed circuit board manufacturer. Their service is ideal for production runs and hobbyists alike. It's very quick and easy to get a quotation if you're prototyping PCBs, and you can get 5 PCBs in many cases, including postage, for around $10. There's also a large shared project section on PCBWay. These are projects that users have uploaded themselves. We can just look at a few here, and I have built a number of these on Learn Electronics Repair. Here, for example, is an EEPROM programmer, and there are many projects on PCBWay's website, thousands of them. So there are lots of interesting things to browse and build here, and you can also upload your projects. Anybody uploading a project onto PCBWay can earn a commission of 10% on all PCBs sold. So this is a great way to get your ideas out there without having to outlay any money on circuit boards that you may not sell. But you may find that your project is extremely popular and you can make yourself some money. PCBWay kindly sponsor Learn Electronics Repair, and that has enabled me to make many interesting project videos this last year. If you're looking for PCBs, give them a try. I'm sure you will not be disappointed. So guys, you've seen now that you can find many projects on PCBWay. They're uploaded by the creator and they get a commission from any PCBs they sell, and if you do the same, so will you. However, it's down to the creator how much information he uploads, whether he just makes the PCBs like this with the components marked the value so you can build it, but you have no information, schematic, Gerbers, or whether he gives you the full information. In this case, we have no schematic, no Gerber, just the PCBs. And because we want to upgrade this, we're going to make the PCB. You've probably noticed next to me is my friend Detlef Amend, who's just moved over from Germany. He's one of the latest inhabitants on the island.
Yep, becoming a Canarian right now.
Exactly, becoming a Canarian right now. So Detlef is, as well as being an electronics project designer, he's also very good with photography and use of software.
Sometimes, at the moment.
At the moment, exactly. So the way I would normally do this is on paper. I would actually take the PCB, paper, and work out the schematic, and then when I'm happy with it that way, I would then recreate that in something like Easy EDA. But we're going to do it the shortcut way. So the first thing we're going to do is take photographs of the PCB. Now, I happen to have the unpopulated board, so I'm going to take one photograph of this side, and as you'll notice, I tilt it, it removes the glare. So we're going to take a photograph like so, without the glare, and the same on the PCB track side. You see I can tilt it there, and we can remove the glare, we can see the tracks. So we have this photograph, we have this one, and we have the built version of the project. Now, if you don't have the unpopulated PCB, you can do almost all of this, in fact all of this really, just with the populated PCB like so. I'm using the overhead camera system because I have it on the bench for the YouTube videos, but you can use your mobile phone or a scanner or any other way you want to take the photographs. So we actually have some we've taken, as they say, some we prepared earlier.
Yep. We did.
We did. So I'm now going to pass you over to Detlef, who's going to explain how we can use Photoshop to overlay all of these images, and then we will have something we can use to actually make the schematic. So guys, over to Detlef, and let's all learn something here, me included.
Teaching the Grandmaster, man, I'm so honored. Yeah, okay, this is something that isn't so much electronic specific. I think this is the first time you see Photoshop on this channel. So we're using Photoshop because I'm familiar with it. So this is something where I go, let's do this in Photoshop because I can show you how to do this. And you can use any software with graphic images processing. Doesn't have to be Photoshop.
Is there any free or public domain software?
Yeah, of course. There's GIMP, but as I told you, I'm familiar with Photoshop. So.
Okay, so
yeah, this is maybe we should do a version where we go for how can you do this without paying the usual amount.
So basically, the ghetto method, ghetto method, how to do this without using any paid software.
Yeah. Guys, if you're interested, in the comments, please.
That's a good idea. That's a good idea. So use what you're familiar with today, and then, like I say, if you guys are interested, we'll work out how to recreate this using completely free software.
Don't look so much on how I do. This is more a thing what I do. This is not how to handle Photoshop, because this was go beyond the scope of this video anyway. So keep in mind, we just look at what I'm doing. I try to explain a bit why I'm going there, and I want to teach the Grandmaster something.
Oh, thank you. Okay, let's go then. Let's go. Yeah.
Okay. First thing I need to do, I need to import some images. These are the ones we captured with the overhead camera. Can I get this bigger? Yeah.
We use VLC.
Yeah, this is VLC, and we exported the snapshots from VLC. So you see, this is the tracks only layout, and we have something where we go for. This is a populated one, and we probably get away with if we only use these two.
Okay.
So we did the upper side, the upper PCB too, but there are no tracks on here, so this isn't that important. So I try to go with the two I know. So
which were actually, if you were taking something like a power supply or some commercial item, these would be the two that you would have.
Right. Yep.
So this is better. Yeah.
And remember, if it's a board with more than 2 layers, this is probably not possible to do this. So 2 layers is the max with this what we're doing right now.
Okay.
First, I import the image. I'm a lazy so I simply grab an image and drop it onto Photoshop, and there you have the image. And now I need the second one. This is the one with only the tracks on it. I'll just simply grab one and drop it over here. And now I have my 2 images.
Okay.
So you remember, because we flipped the PCB to do the second image, so we have to flip the image from the PCB to put it on the.
So you're saying that this is a mirror image of this one? Yeah. Okay.
And since let's see, there's the potentiometer, there's the USB thing.
Yeah.
So we have to flip it. This way.
This way.
Yeah. All right. In Photoshop, I have to do a copy of the background layer. I simply draw it down here onto the new layer. There's a copy. We can use this.
Is that because you can't edit the background layer?
Yeah. The background layer is something special. You can unlock it, but this is the
this is the easy way.
Lazy. Because now I can simply go for edit, transform. Where are you? Transform.
Transform is here.
Yeah, thank you. I'm used to keyboard shortcuts, and Richard told me, don't use this keyboard shortcut so much.
I did actually ask Detlef to show you using the menus. So if we struggle to find anything, that's my fault, Okay. Blame me.
Yeah, I do. So, and if I go to edit, transform, and use anything, scale is okay, because I wanted to have the right-click menu here, and so I can say flip vertical, and whoop, there you go. Now we have the potentiometer on the right side. There I see on the left side is the USB port. There's the power transistor.
Oh, this, okay, yeah, so we can see it.
Yeah, so now, oh crap. I shouldn't say that.
No, I'll have to bleep a lot of this, guys.
Sorry.
It'll be fun.
Yeah, and what I just did, I simply grabbed the new layer, moved it onto the image with all the components.
And
what I'm doing now, I'm used to work in full screen, F for full
Okay,
screen.
fine.
Simply type F on the keyboard. I don't know if there's any shortcut here.
But F on the keyboard is full screen.
Yeah.
Okay.
So now I don't have the thingamajigs around here.
Okay.
And I can move this with this tool. This is a move tool.
Okay.
And I simply move the image around here. And let's see if we can line it up together.
But to do that, we need to see both images.
Yep.
Okay.
There's a thing for all the layers. You can simply use a layer and use opacity over here.
And make it more transparent.
Yeah. Pro tip: you can use this number here. There's a drop-down menu here with this, or you simply click on the word opacity. Come on, you click on the word opacity and move it left or right. So you simply see both of them.
I was going to say where is it gone, but
and the mirroring didn't translate. I don't know where I did this wrong. This is always when you're on camera, something doesn't work. All right, let's do this in here. This is no problem. We simply go for edit, transform, scale, right click, vertical, flip vertical, and it's
now it's worked.
Yeah,
I can see.
Yeah. So the SMD resistance must be down here. Yeah. So we angled this one. We did this because we wanted to have the maximum contrast on the tracks, and
we had a lot of reflection from the overhead lighting,
so we
guys.
Probably have to do some tweaking in here.
Okay.
All right. Now I have this probably position somewhere and go down with the opacity to 50%. And let's see if we can get this aligned. This is not bad.
That's not bad. No,
that's not bad at all. All right, this was easier than I thought.
It's out of line on the resistors. I can see a little bit. Can you drag that the height?
Yeah. This is transform again.
Okay.
Edit free. We can use a free transform for this one. So now I can. If you want to have this proportional, there's a lock over here. So now my image would be scaled always proportional.
Oh, I see. That's a stretch.
Yeah.
Yeah, and that's better. Yeah. Straight away I can see that's better.
And if we don't want to have this proportional because there's an angle on one of the images, we simply unlock this, and now I can move the image free.
Oh, I see. Yeah. Okay.
Yeah. And from here on, well, that went fast. Okay, I thought it would take longer, but it looks like it's pretty much on the point. Look at this.
Yeah, it is. Yeah. It is. Yeah. I mean, the IC looks slightly out of line with the holes, but does that? I don't suppose that matters as long as we know there's an IC there.
Right.
We can see which is pin one.
We know where the pins are. Yeah.
So the only thing I have a problem with that is it's not very easy to see the blue tracks against the blue background. Yeah. Can we do something to make that a lot more clear?
Okay, let's try if we can do that.
Okay.
I kick up the opacity so we know what we're working on.
Okay. Okay.
Yeah.
Oh, I see.
So this is the image right now, and I want to go for some curves. Curves is this is the tool. Don't use anything else. Curves, and in here, this one here over here is the representation of the brightness levels in the image. So here's black. There's white. And you see the line in here. This is where it gets calculated.
Okay.
So I want to increase the contrast. This is why we took the image that way. Yeah. We wanted to have a difference between the tracks and the PCB.
Yeah.
And you see it in here that the tracks are slightly brighter than the background.
Yeah.
And I can use this.
Okay.
So there's this symbol over here. This is a finger who pushes. I don't know. I have no clue how the designer at Adobe would describe this.
Click and drag. Okay.
Yeah,
the finger that pushes.
But there's an explanation there. And the interesting thing is you simply click on this part and move it up so I make this brighter.
Okay.
And I want to do the same with this one. I want to make this darker. Yeah. And suddenly there's a PCB in there.
Hey guys, this is the man, yeah. When Jet said he could show me how to do this better than paper, he was right. Yeah.
Yeah, so this is the lazy way.
Okay. I may have to bleep that.
Dang it. It's okay. This is my eyes hurt a bit for the colors, so
that's nice.
I turned down the colors a bit. This is hue saturation.
Oh yeah,
Yeah, so I bring down the colors a bit, so because all the noise in the image pulls up too, because and I don't want to have that. I want to see nice tracks in here. If I want to change the color right now, I could just do with a hue slider. We do this in a different way.
Okay.
In a second, I'll go back to the original.
Okay.
Okay, this is quite nice for the starter. There's a way to, you know how they do this in comics when you have a rough draw and you want to get rid of the pencil in the background. There's a threshold command.
Okay.
And I try to use this now. This is another layer in here. There's a threshold.
Threshold. Oh.
No, this is not where I want to go. Just give it a second. I want to go there. Now we have tracks.
Yeah, now we have tracks.
Yeah, now we have real tracks.
Can we get rid of the screwdriver thing that's at the top, like off the PCB?
Yeah, we could.
Not that it really matters, but I just thought.
Yeah, this I think is a pretty good start. Now I want to bring all the layers into one layer because I don't need all this fancy stuff over here. So select them all. This was holding Shift, and this is just like in Windows when you select files. Yeah. You simply can click on one and hold Shift. And press the other one. So you have them in a stack, and now you go for Control E, and I have no clue how this is. Where is this in the menu? So forgive me to use Control E.
It works.
Yeah. And now I have one layer with all the information in here.
Yeah.
And now we do some cleanup.
Okay.
We can do this in a different, in this way. The easiest way is to grab a rectangular selection. Okay. And everything we don't need. So we won't need that, right?
Yeah.
We could fill it with a color, but the other way around, we could simply delete it.
Okay.
There's a delete key on the keyboard. Okay. So
it's just gone.
Yeah, it's just simply gone, and can clean up this a bit.
Okay.
And clean up the lower parts a bit.
Okay.
And well, while I'm on it, when in Rome.
Okay. Yeah. Okay. That's looking a lot more like a PCB.
Yes, it starts to look like a PCB, like a very, very strange one. Yeah.
Yeah. Okay.
There are image calculation modes in here where you can say how do I want to superimpose the image I have in front onto the rest of the PCB. So this is a way to do this. We could use this.
Okay.
The problem right now is we can't change the color, and I probably want to change the color for that. Yeah. And the easiest way to do this is to select a color from here. Okay. So if I grab anything that's white, I can do this by select, color range. And if I click in here on everything that's white, let's give me a selection from everything in here that's white. It's clean white. There's a slightly fuzziness, so you have some gray areas, but this is probably a good representation. Okay. And you see it says a selection. And what I do right now, I convert this into a solid color layer. Okay. Why do I do this? Because I can change the color for this. Yeah. And if I remove this layer, we only are left with the tracks. Yeah. These are only the tracks.
You've removed the black layer now. Yeah.
Now we have only the tracks in here. And for visibility, we can change this too. Man, this makes me aggressive. Let's go for some cool blues or some calming blue greens.
Okay. Yeah. So can we... I mean, that's working, but can we make the PCB look like it's behind the resistor so we can see the color codes on the...
That's where the opacity comes
okay.
in. Yeah. So we'll simply go for opacity here, and now we can see where everything goes.
And we can read the resistor codes.
We can read the resistor code there, visible to, where's our power leads coming from here. You can always hold the key, the space key on your keyboard, and you can simply move the image around. And I think... Well, grandmaster of everything here.
No, I think that's it. I think that's it. So
I think we can use this.
I think we can use this. So we're going to have to create a schematic now from this, and like all the lines, if I move back, so like each one of these tracks is a net in Easy EDA. So if we print this out, I think we only have one screen to work on these guys. I do have a dual screen set up, but I can't capture from both, and you guys need to see. So I'm thinking if we print this out, we can effectively use a pen to mark each net. And then we can draw it in Easy EDA between the components.
Yeah.
And that should then give us a schematic, I hope.
Yeah, yeah.
Yeah.
You could do this, of course, you can do this with pen and paper, but this way we are sure that we have that all lines in here, and we simply cross them out while we go for it.
Yeah.
If you ever do a screen setup, you can, for example, use simply redraw or everything that you put into the schematic. But this YouTube has to have a dual screen setup.
Exactly. Yeah. So printing this out, I think, is the way to go.
Yeah,
and then
that's how we're going to do this.
Let's try it. We've not tried this before, by the way. Or I haven't. Have you done this before, Det?
Not in this scale.
Okay.
I already converted some images for that because I wanted to have some schematic for that. I wanted to understand how this is done.
Yeah.
This could be a whole reason to do this for simply understanding what's going on there. And in fact, I think the author here, this is nice that he published it. But if you publish stuff, man, put out the schematic.
Here.
Yeah, because it's reverse engineerable.
Yeah, maybe he just wanted people to buy his PCBs at the end of the day. Yeah. But actually, just looking at this, what we have on the screen now, even if we didn't then go to create a schematic because we want to modify this project, if you guys were working on something with a double-sided board, and we could have another layer with the front tracks superimposed like this, if you just got this far with it on, say, a power supply repair or something, it's very easy to see here what's connecting to what.
Yep.
Yeah. I think that's even in itself is a result.
Yeah. One thing to add, if you would do this with a 2-layered board, you would go the same way we did just, but you would choose a different color for the front side and the back side.
Yeah. And the only other thing you would probably have to do is, for example, unsolder the ICs where tracks are going underneath them, so you can see where they go. Or if you don't want to do that, just effectively meter them out. So then you can draw in the blanks if you can't see this section of it, but you know that pin connects to there. Then you can draw this in yourself. Yeah, and here. That's great, Det. Okay, so we'll get this printed out, guys, and then let's go over to Easy EDA and see what we can do.
Go!
Yeah. We've printed out the image from Photoshop. So this is the one we printed in grayscale to see how it would look. And here is one in colour. And you see I've been writing on this one. Now, the reason I'm writing on this is because there are no component numbers on the actual PCB, but we have the component values. When we added these components to Easy EDA to make a schematic, we had numbered them R1, R2 and so on, and it just makes it easier when we're actually drawing the tracks what connects to what if we write the component numbers on here as well. So we're not thinking, okay, what was this R6, was it R5? Once you start to confuse things, you'll confuse yourself and it'll all go horribly wrong, yeah?
As it does.
So we have that. Now, I noticed that it would have been easier for us to actually have created a negative version of this, so it was easier for me to actually write on the printout. And that will just show you actually how we can do that.
Okay, back in the magical world of Photoshop. This is the one we printed off. And if I wanted to do this as a reverse one, because it's really hard to write on something because we don't have any white pencils over here. You could choose another layer effect. So there's an invert layer. So simply this inverts stuff.
Well, that was horrible.
Yeah, this looks like a radiation. I
can see that.
Yeah. So of course now all the tracks are bright. So I'll go and make the tracks dark. So I can do this. Yeah. If we go down with the color, this starts to look like something we could use.
Yeah, absolutely.
Yeah. And now you could write on it.
Yeah.
Even you could get rid of the color in here. There's a hue saturation layer here. If I get rid of the color on the one below, that could help too. That depends on your image.
Yeah.
This is not something where you say, well, use this, use that. Use common sense. Yeah. When it looks good and you can see the tracks, that's the way to go.
Yeah. This will depend a lot on the PCB.
Yeah,
of course.
Yeah. If it's a green one, that's a bit different because you have different color schemes in there.
So now we'll go over to Easy EDA and let's start to create our schematic. You might have noticed, guys, we've actually disappeared from the screen. That's so we have enough space to actually show you what we're doing here and we're not covering up anything important. So this is Easy EDA. I made 2 beginners tutorials on this, which I will link from this video. So we're not going to go into the absolute beginning part of it, but you'll be able to see if you watch those videos how to do what we've done. So what we've done here so far is added all of the components onto the sheet. We have them there. And now we have to draw in all the tracks where everything joins up. You'll see on the desk here I have the printout, and this is why I was mentioning I have the component numbers on here that match the ones we have here, so we know which part goes where. You'll see all these light blue tracks, so these are what are called nets in Easy EDA. You'll notice this one which goes everywhere. This is the ground net. We also have the power net, which goes a lot of places, and then we have smaller ones. So what we're going to do first is put the ground and the power nets in, and then we can move on to the other ones. I'll just draw this on the paper, so you'll see from here. We have this is all ground net. You can see where I'm joining up. And if we do it this way, we're not going to get lost. We're not going to miss out anything. So you can see it comes down here to here, to the end of this resistor, and it goes down here to our chip. So we're going to draw that net on the schematic, and to do this I'm going to hand you over to Det, and then we'll do the similar things with the other nets.
Perfect. Okay, Richard will be my eyes and ears on the schematics, and I do the computer stuff again. And yeah, I'm pretty lazy with that. For my nets, I always use the net port. This is this symbol here. And I simply, this is already GND over here. Yeah, you can use the specialized symbols over here if you want to. You don't have to. If you have multiple GNDs or multiple VCCs in here, this is something that gets out of hand pretty quick. So yeah. I normally stick to the net ports and give them the right names. You even can change the color.
So that will effectively connect all these points together without us drawing and that's nest of lines on the screen. Yeah.
To me, this is way more
elegant.
Elegant, that's a good word. Yeah, way more elegant.
A good English word.
Yeah. So right, let's see where we need to get ground. Ground is of course at the USB port, and if you're an Easy EDA and you simply drop the net port here, you don't need to draw a line. If I draw the port right here, it already has a line in here. So, so this keeps you from drawing lines here. And now I've moved it too far. So there it should go. From here on, I simply go, I click it on, I use Control and C for copy.
Okay.
Now I can use Control and V, and now I have another GND. Yeah.
Okay.
Yeah. So now where
I need to tell you where this goes. Okay.
Yeah, you're in control here.
Okay. So guys, you can see that Det has already put it on pin 4 of the USB port. So that GND goes to one end of R2.
R2. Okay. I'm going to move R2 for this. This will build a schematic by itself right now. Okay. If I drop this in here, I go for GND and use W for wire and draw a thingamajig like this.
Okay, and we have it.
Yeah, and now we have R2 with a lower pin connected to GND.
And I've marked that on the
and
printout, as you can see.
It's important to keep your tracks on the printout. If you do this with 2 people, this is so much easier.
Yeah, absolutely. I can see that already.
Yeah.
So it goes to one end of C1.
Okay, C1. This is a 100 nano.
This is, yeah.
Yeah, rotate and do the same here. Grab the GND.
So I think you can see, guys, why we marked the component numbers on this piece of paper, yeah?
Yeah.
So we have there. I'm literally just putting a coloured blob every time I see somewhere it goes. So it goes to pin 4 on the IC, U2.
Yeah. Now I can simply press Control V because it's still in the clipboard. And every time I press Control V, I get another of the GND connectors. Use W to get a wire tool, and then you simply put in a wire there.
Okay, and we keep going. So it goes to one end of the potentiometer.
The potentiometer is right here.
Yeah, so one of the ends.
Yeah. And you probably notice we don't know what the schematics will be because we're simply following lines here.
Yeah, absolutely.
Yeah. So I use the lower ones with that one wire. And remember, everything we connect here is in fact one big line. But you can imagine if I have to draw lines here all over the place, this would look like a mess.
Yeah, absolutely. It's a good idea. I didn't think of this like you were thinking of it. It goes to one end of R0, which is a current sense resistor.
50 mil, all right. Control V. Okay. And I simply drop it here and move it a bit just for optics.
And while Det is doing that, I'm just following the track round now to all the through holes to see if I've missed anywhere this track goes to. And I haven't. That's everywhere it's going.
That's
to.
Everywhere G&D is.
Okay, so the next one we're going to put in is VCC power.
Yep. Should we call it 5 volts?
We can call it 5. No, because this load can actually work on voltage up to about 35 volts.
You're right. The op-amp is the only component here that limits the supply voltage.
And the TL431, I think.
Oh, yeah. The TL,
yeah. So
the 5 volts is something arbitrary. It doesn't need to be.
So we just call it VCC.
Okay, just go for VCC.
And we can start with pin 1 of the USB connector.
That's a nice one. Okay. I simply Control V in another ground point and simply rename it by double clicking. It just was a simple double click. VCC.
Okay.
And now I can copy this again. Now I have it in my clipboard and simply drop it in here. Drop it in here. I can do that.
Okay.
Yeah, connection is there.
We have one end of the R1, the 2 meg resistor.
R1 is here.
So you can see, guys, I'm actually drawing this where it's going to.
Wire and connection is, come on.
Okay. It goes to one end of C1.
C1. Oh, this is a decoupling.
The decoupling, yeah, directly across power and ground.
Yeah. Wire.
Okay.
If you're wondering why my voice sounds so rough, we got Carnival here.
Oh yeah, guys, you see it on the other video, yeah.
Better not.
It goes to pin 8 of our ICU2.
Oh yeah, that has to be. Look, this is the power pins for the op-amp, so this must be somewhere here.
Okay. It goes to. I just need to check this. You see where we have these red wires here? No, we're not covering the track. I can clearly see.
Yeah.
It goes to the collector, which is the middle pin on the TIP122 Darlington transistor.
Yeah. You see the Q1, the symbol here is a Darlington. It doesn't say collector base emitter, but it's collector base emitter.
Okay.
All right. VCC.
That's the collector.
Wire. And got it.
And that's it.
All right.
That's it for that one. So, shall we draw in another net? Do you want to give us a name like now, net 1 or something?
We can do that, yeah.
Or we can have a random name. So we're going to draw these in, guys. So we have one net that goes. This is quite a long one again.
Okay, that's a good one. So we can give it simple numbers and 1 and stuff like that.
So this goes from pin 5 on the U2.
Just a sec, give me N1.
Okay.
From
pin,
U2?
From U2 pin 5.
Gotcha.
Okay.
Yep.
It goes to one end of R6.
R6.
Okay. And then it goes to one end of R5. Okay. So we have the next track then. This is easy. So we have one net, another net. So this is N.
N2.
Oh, one moment. Let me just check. Yes, N2. And this goes from R2, the end that we haven't used already of R2.
Over. I see you. Oh, yeah.
This goes from R2.
Yeah. And don't forget to rename the net.
Otherwise, we're connecting things together we shouldn't be doing.
Wouldn't be good.
Okay.
Not recommended.
That goes to, is it possible to get to auto name them if we wanted to?
I think it is.
That's for the advanced video.
Never use it.
Okay. So guys, you can't see the fingers, but comments below.
Comments are going to be below, please.
Okay. So one end of R2 on N3 goes to one end of R3. Oh, sorry, N2. Sorry, on N2. Yeah, one end of R3 is on N2.
Yeah. Okay, got it.
And also pin 6 of our U2.
this is N9. This is going to the tip. Yeah.
R7, yeah, that's going to there. And the other end...
N5, yeah, net 5.
Net 5, well, net 5 also goes to pin 1. Is that right?
Yep, it is.
That's perfect.
You did it.
Nice. You got it. Okay, guys, so actually we now have all of the tracks on our schematic. And although this doesn't look much like a schematic, we could actually now use this to make a PCB.
Yeah.
And modify it. But we want to be able to make this look more like a schematic so we can add to this project. So that's the next step, yes, Dad?
Yeah, right.
Okay, so how are we going to do that?
Yeah, so I'll simply, right, this is boring the other way around.
Okay.
And I only have to keep an eye on, I can't delete this. Because if I delete this, there's probably a connection that would be needed. And it still has to be N1. But I've already moved everything.
Okay, yeah, so we have that.
This looks way more like a resistive divider than what it was before.
It does.
Yeah, and I should stop fiddling around here.
Yeah, probably.
Yeah.
Know when to leave it alone. So, Det did a really good job on that, just by moving things around.
No, come on. You helped a lot.
Okay, it was a bit of a joint effort. We will agree it was a bit of a joint effort. And we actually missed one net, which was this one, from the feedback resistor. But when I looked at how this worked, I realised something was missing. So what we have here, if you look, guys, we have this TL431. When it's wired like this with cathode and ref connected together, this is a fixed 2.5 volt reference. And that connects into the op amp, this part of the op amp. And we have an output from this op amp coming to the potentiometer. Now, these two resistors, R2 and R3, actually set the gain. This is an amplifier. So this is amplifying the reference voltage and putting that across the potentiometer. This is just a filter capacitor to stop noise when we move the slider, I would think. So the voltage on the slider will depend on the position, and that comes into this part of the op amp input on 3. You'll see we also have an input on 2. Now that one, and this is where I realise something is wrong, that samples the voltage across the current sense resistor. And the output of this op amp drives the transistor. So the amount of drive on the transistor, the amount of current that's flowing through it, through the current sense, depends on the position of the potentiometer. Yeah, the higher we put this, the more current needs to flow here to get more voltage across here to balance the op amp. And that's really how this works. So that we now have a schematic, and you can see how that was done using the nets without making a big mess. And then it was just a case of finding each net, searching for how many times it's occurred in the schematic, and bringing them together.
Yeah.
So from this, we can do two things. First of all, we can easily create a PCB, but the other one, we can actually now add to this project. Okay, guys, I hope you enjoyed that video. So now you know how to take a PCB and create a schematic, which you can now use either to design your own PCBs or to modify the device, or if you like, you saw the first part of this where we just took a populated PCB, could be a power supply, something you want to repair, and make a nice image that effectively shows how it's all laid out to make it much easier to diagnose faults on that. I'm not sure this has been done on YouTube before. We were discussing, we think this is a bit of a different technique, so maybe something a bit of a first on learning electronics repair. Now we've got as far as making the schematic, there are a few ideas we had in mind for this project. So we're thinking we can upgrade this. I was using this on a video. Again, I'll link to this one for the actual USB load. I was using a separate USB power analyzer to monitor the voltage and current. But we could put that on here, so I don't think, and Det agrees with me, it would be too much of a problem to add a daughter board on this with a display displaying volts, currents and watts. So as you adjust it, you will see that readout,
Yeah, with a little microcontroller on that to do all the math on that.
Yeah, so we think that should be quite easy. And especially so now, because we have a schematic for this. The other idea we had in mind was to add the facility to control a PD USB power supply. These are the ones which will switch between 5 volts, 9, 12, 20. So you can manually switch.
Yeah, because the hardware already can handle up to 20 watts.
Exactly, yes. This load will have up to 35. And we can also add a separate input on this, banana sockets, so you could load anything with it. We think that would be useful.
Yeah. This won't restrict the use to USB, because this is easy. Just add 2 parts.
Exactly. And to keep the cost of this low, we want to leave this as a usable version, but add the connections on for a daughter board. So the daughter board will A, give you the option to display the parameters, voltage, current, watts, and B, the option to actually control the PD USB power supplies. And we think we can make that so you can effectively half populate the board just for the display and populate the other half if you want the PD control. So only thing really to say now, guys, is 1, did you enjoy that? 2, do you have any other comments or suggestions on our suggested modifications?
Let us know.
Yeah, in the comments below, guys. Let us know what you think. And lastly, I'd just like to say it was a great pleasure working with Det today.
Thanks for having me.
You're welcome. But Det has skills which I don't have. He's teaching me as well. I actually learned a lot from there. And he says,
listen to him.
and he says, I'm the master. Well, maybe there's another one here, guys, yeah? So, only one more thing to say, and that is adios, amigos. Bye for now.
Bye for now.